Thank you for watching our video. In it we'll present a novel artificial intelligence technology for predicting glaucoma progression. Glaucoma is an eye disease where photosensitivity of the retina is decreased, leading to blindness due to damage in the retinal nerve. Vision lost in a glaucomatous eye cannot be restored. However, medical treatment can slow down the progress of the disease to prevent further loss of sight. To balance risk and benefit from treatment, we need to accurately predict photosensitivity in the future. This task can be formulated as a regression problem using past measurements using perimetry, such as the Humphrey field analyzer, to estimate future photosensitivity. We want to use as small a number of measurements as possible. Firstly, because measurements of the Humphrey field analyzer are very costly. Secondly, it might be too late for treatment if we wait for large numbers of measurements to be collected. Accurate prediction in this setting is very challenging because the measurements can be very noisy. How can we overcome this problem? Our solution is to utilize additional information. Retinal layer thickness can be used for additional information because glaucoma reduces retinal layer thickness. Recently, optical coherence tomography has been adapted to measure retinal layer thickness, which is less labour-intensive, less noisy, and less time-consuming than visual field testing using the Humphrey field analyzer. Retinal layer thickness measurements are obtained as images like these. If retinal layer thickness measurements are successfully integrated to photosensitivity measurements, prediction of future photosensitivity is expected to improve. However, there are two challenges in integrating retinal layer thickness and photosensitivity measurements. The first challenge is data heterogeneity. The dimensionality of retinal layer thickness measurements is higher than that of photosensitivity measurements. Each retinal layer thickness measurement can have several channels, whereas each photosensitivity measurement has one. The second challenge is temporal heterogeneity. Retinal layer thickness measurements are typically obtained at different time points to photosensitivity measurements. Moreover, both types of measurements are performed at irregular intervals. To overcome these two challenges, we propose a novel technology called latent progression patterns. Through experiments on real data, we have demonstrated that highly accurate prediction can be achieved using both retinal layer thickness and photosensitivity measurement sequences. As a result, a less costly and more efficient method to detect glaucoma at an early stage is made possible.